Hey guys, I bet you thought we had done all we could to make sinusoids more and more complicated, but there's one additional thing we can do, and it has to do with shifts inside the function. So we've already talked a bunch about shifts outside the function, like if you add or subtract something outside the function, that shifts the whole graph up or the whole graph down. So a vertical shift will change what's called the equilibrium. You could also have a shift inside the function. You could add or subtract inside the function. And as you learned when you talked about function transformations, what that does is it shifts the whole graph forwards or it shifts the whole graph backwards. As opposed to being a y shift, a shift inside the function is an x shift. The one thing you have to be careful about there, though, is that inside the function, changes are always counterintuitive. So if you have something like -5, that actually shifts the whole graph forwards 5. So that's what we're going to be talking about today, getting our sinusoids to shift forwards and backwards. So the first example we're going to do today is we're going to graph y equals the sine of pi over 8 times the quantity x minus 5. Notice I made no changes outside the function. I did not change equilibrium. I did not change amplitude. So this is just a typical sine wave, which a typical equilibrium at 0, a typical amplitude of 1. I've just changed the period, and then I've shifted the graph. Okay, so let's start off by figuring out the period of this graph. We know that the period is always 2 pi divided by the b value. So in this case, it's 2 pi divided by pi over 8. Because I am dividing by a fraction, I want to multiply by the reciprocal. So divided by pi over 8 is the same as times 8 over pi. The pi's cancel, and the period for this function is 16. And for those of you who are interested in the quarter period, how long it takes to get through a quadrant, that is going to be 1/4 of 16. 16 divided by 4, which is 4. Okay, so if I didn't have this x minus 5 business, I would just draw a typical sine wave, but I would make the whole cycle take 16 units. Here's what's a little different here. This graph has x minus 5 in it, which means that the whole sine wave has moved forwards 5. What does that mean in terms of your graph? Well, when you go to graph this function, what I'm going to say is instead of having the sine cycle just start at 0, the sine cycle is going to start 5 forwards. So I am not going to start my graph right at 0. I'm going to start my graph at x is equal to 5. I'm going to draw a complete sine cycle starting at 5. So it goes up to the top, it goes back down to the middle, it goes down to the bottom, it goes back to the middle, with a typical equilibrium of 0 and an amplitude of 1. Okay, so the cycle started at 5. Cycle starts at x equals 5. And in case you're scratching your head and being like, wait, Ms. Ball, why did you start at 5 instead of -5? It's because inside the function is counterintuitive. So x minus 5 actually moves it forward, so the cycle starts at +5. Okay, now, how do I know where the cycle ends? That's where the period comes in. Period is basically a measurement of how far you go from the start of cycle to the end of cycle. So in that I've got one full sine wave here, this needs to be one full period of 16 units. So if you were curious as to where does the cycle end, the cycle ends one full period later. So it should end 16 units later at 21. All right. Does that make sense? Yeah. Let's think about our quarter period. The quarter period is how long it takes to go to a sort of special point. So 4 units after 5, I would be at an x of 9. 4 units after that, I'd be at an x of 13. 4 units after that, I'd be at an x of 17. 4 units after that, I would indeed close out my period at 21. So the cycle started at 5, it ended a full period later at 21. It turns out, though, these graphs, of course, go forever forwards and backwards, and that means you could keep going with this graph if you wanted to. So, for instance, I could say, I know that the next maximum is a quarter period later at 25. If I wanted to backtrack, I can actually say I have a minimum here at an x of 4 backwards, or 1. I could go a little further backwards. I'd be back at equilibrium at 3 back, or -3. So this graph goes forever forwards, forever backwards, repeating that pattern. But the really important thing that happened here is that my sine cycle got scooted forward 5, so I start one of my cycles at 5, and I end one full period later, in this case at 21. So that's the sort of change we're going to be working on today. I'm going to give you 2 more examples where we've got a whole bunch of crazy stuff going on, and we'll try to keep track of all of the pieces. All right, so how about for our second example today, we try to graph the function y is equal to 2 times the cosine of pi over 12 times x plus 2 plus 5. So we have 2 changes inside the function, 2 changes outside the function. Let's do the outside function changes first. So we have a vertical shift of 5. So that tells me my equilibrium line has vertically shifted up to be y equals 5. And I have a vertical stretch times 2. So that tells me my amplitude, my stretch from the center, is going to be 2. All right. So why don't I set up my vertical boundaries first? I'm going to draw my x and my y axis. And I will label my overall average output up here at, let's say this is 5. And if the amplitude is 2, that means I should be able to go 2 above that to 7, and 2 below that to 3. Okay. Now, the inside the function stuff, that's a little trickier. This graph has a b value of pi over 12. Therefore, 3 little dots in a triangle means therefore. Therefore, the period of this graph is going to be 2 pi divided by pi over 12. Dividing by a fraction means multiplying by the reciprocal. So divided by pi over 12 means times 12 over pi. The period of this function is 2 times 12, or 24. Meaning the quarter period, how often I will finish up a quadrant, is a fourth of that. The quarter period is 6. Okay, so now on to the actual graphing. I'm graphing a cosine wave, so I know I start at my maximum. Where do I start? Well, normally I would start right here at the y-axis, but the issue is that I have a shift. This graph has a +2 in it. What that means is that every single x value got scooted backwards too. So my cycle actually starts at x is equal to -2. Why is it -2, not +2? Because the whole graph moved back 2, because it's counterintuitive. So at an x of -2, that is where I start my cosine cycle. Cosine starts at its maximum. All right, how do I know where that cycle ends? Well, the cycle ends precisely 1 period later. We concluded that this graph has a period of 24. So if you add 24 to this, -2 plus 24 is 22. That means a full 24 units later, let's call this x of 22, my graph has finished a full cosine cycle. I'm back up at maximum. So this graph is going to go through 1, 2, 3, 4 quadrants worth of behavior. It's going to continue forever forwards and forever backwards. And it started its cycle at -2. It ended that cycle a full 24 units later at 22. And if I wanted to know where all these intermediate points are, I could just add the quarter period. So if I add 6 to -2, this point is at 4. Another 6 later, this point is at 10. Another 6 later, this is at 16. 16 plus 6 does indeed end my period at 22. Lovely. All right, let's do one more of these together. Okay, so last example for today. We together are going to graph y is equal to -3 times the cosine of 1/2 times x minus 6 pi plus 10. If you're feeling really confident, you could actually pause the video and try to get this one set up for yourself. I'm going to say I know the vertical stuff is easy because anything outside the function is really intuitive. So my equilibrium line is at y equals 10. The amplitude of this graph, the stretch away from that, is 3. So I'm getting started with my graph. I can draw a little x-axis and y-axis. And I can make my average output 10. I know this graph stretches 3 above that to 13, and 3 below that down to 7. All right. In terms of my inside the function stuff, my b value is a half. Therefore, the period of this function, the length of the cycle, is 2 pi divided by a half. Whenever I divide by a fraction, I multiply by a reciprocal. So the period of this function is 4 pi. Meaning the quarter period is actually really easy. Let's call it the QP for now, the quarter period. I'm going to finish a quadrant, 1/4 of that every pi units. All right, and so then the one new thing for today, this graph, instead of starting right here at the y-axis where we typically see graphs start, this graph has a shift of minus 6 pi, meaning the whole graph moved forward 6 pi. So my cycle is actually not going to start right here at 0. In this particular case, the cycle starts at x is equal to positive 6 pi. If it says minus 6 pi, your cycle starts at positive 6 pi. Inside the function, counterintuitive. So let's say that this is 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. Let's call this 6 pi right here. All right, so that's 6 pi. And notice there was that negative out front. That negative did not impact the amplitude. What that negative tells us is that we're graphing a negative cosine cycle. Negative cosine cycles always start at their minimum. So I'm going to start my graph down here at the minimum. Alrighty, so how do I know where the cycle ends? If the cycle starts at 6 pi, the cycle ends exactly 1 period later. The period for this graph is 4 pi. So if I add 4 pi to 6 pi, this cycle ends at 10 pi. So here's 7 pi, 8 pi, 9 pi, here's 10 pi. That is where I expect the cycle of this graph to end. Always end your cycle in the same place you start, because these are periodic functions. They repeat themselves every period. So if you start at the minimum, you'll end at the minimum. All right, so the quarter period is pi, meaning that at each pi, so here at 7 pi, 8 pi, and 9 pi, I'm just doing something special. So I'm going up to the middle, up to the maximum. Oh my goodness, my board broke. I bet I can fix that by tomorrow. Back to the middle and down to the bottom. And so I get a nice little negative cosine period right there. Oh, that's lovely. And so guys, remember, you can totally sort of like backtrack forwards and backwards because these graphs go on forever and ever and ever. This has this really nice quarter period of pi, so I can go like back, 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 back. I'm gonna have another cycle here at 2 pi. And if I keep going back, I've got pi, 0, negative pi. I'm gonna have another cycle end at negative 2 pi. If you want a tip about graphing, just as a quick by the way, your graphs should always be happy faces below equilibrium and sad faces above equilibrium. So if you're having trouble with sort of the curvature of this, these are curvy graphs. They're not pointy graphs. They are always happy below equilibrium. They are always sad above equilibrium. All right, so I promise that's actually all the different pieces that could go into making a sinusoid. The one new thing for today is that horizontal shift. Just remember that because it is inside the function, it's counterintuitive. So if you see like minus 6 pi, your cycle actually starts at positive 6 pi. And then you always want to add the period to figure out where the cycle ends. All right, good luck.